So, okay, so it's a pleasure to have Assaf Naor from Iran, and he will tell us about the nonlinear Dvoretzky theorem.
Okay. So I have 5 minutes to describe the things that Sanjeev knows, right? That's okay. So the story starts with the 1960 theorem of Dvoretzky, which answers actually, at the time, it answered what was for a while before a conjecture of Grothendieck. It's quite amazing that he conjectured this fact. And the theorem is as follows. Probably most of you know it. It says that for every number d bigger than 1 and for every integer k, there exists some integer n, which depends only on these two parameters, such that for any n-dimensional normed space, X, there exists a subspace Y with two properties. First of all, it's big, so dimension of Y is at least k. And two, Y embeds into L2 with distortion D. Let me just explain what this means. So whenever if I have two metric spaces, xd, and maybe I'll give other names. So I'll say that U embeds with distortion D into V. I'll use this notation if there exists some scaling factor, lambda, and I'm mapping F from U to V such that the distance between 2 points is at least, this is in V, okay, so lambda.
D has to do something. It has something to do with this.
Lambda is just, in the case of normed spaces, which will be most of what we talk about, you can just rescale F by lambda and you can delete it.
Oh, okay.
But otherwise, we just say that I allow myself first to multiply the metric by some constant, and then I embed it up to a factor D. Okay, but it's going to be irrelevant until probably the very end of the talk. You can ignore this if you want.
Before I go on, so you call distortion, it's built into distortion that you can first.
Yeah. Taking a metric space and multiplying by 100 doesn't distort it.
Okay.
It just rescales it.
All right.
Okay. Okay. So here's the statement. The statement says that if choose your favorite number, your target distortion, choose your favorite dimension that you want, then there is an n such that if I hand you an n-dimensional normed space, just the fact that its dimension is big enough means that somewhere inside there is this k-dimensional subspace, which is Euclidean up to your favorite error. And I will, there is a whole history behind this. There are many open questions, for example, and there is the D, when D is 1 plus epsilon, or D goes to infinity, when D is 1 plus epsilon, there are major, probably the biggest open problem in the field is that people really don't know the dependence on n. There are exponential gaps between the two things. These are all things which are for a different talk, but this is the motivating theorem or phenomenon that starts the story that I'm going to tell you. And what I want to tell you about is metric space versions of this. And this also has a long history. so there are what's called the nonlinear Dvoretzky problem. This is due to Bourgain-Figiel-Milman from '85. And it's the following. So given, again, a target distortion D, so what is the largest M such that any n-point metric space say X has a subset Y with, again, Y is big now in terms of cardinality, M, and 2, Y is Euclidean up to your error that you prescribed. Okay, so this is a finite analog of this phenomenon if we replace the being big in terms of linear dimension by just containing many points. Now, I will discuss probably the first half of this talk. I will discuss this problem. Some might argue that this is natural, some might not. Y is the number of points, the analog of dimension. The main justification is that, as I hope I'll convince you, there are interesting theorems and many interesting applications. But this objection is actually a good one, because in 2005, Terry Tau asked what's so this is, let's call it Tau's nonlinear Dvoretzky problem. He just suggested a different metric analog of the same question. And his suggestion is in many senses, I think, more natural. You just look at the original Dvoretzky theorem, and you just keep the statement as is, just interpret the dimension in the correct category. Okay, so you can ask the same thing. So given D, your target distortion, and n bigger than 0, doesn't have to be an integer anymore, what is the largest alpha such that any compact metric space X of Hausdorff dimension at least n has subset Y with, again, Hausdorff dimension of Y. At least your alpha, and 2, again. Okay, so this is really keeping that statement, and just, well, in metric spaces, dimension has a natural meaning, which is Hausdorff dimension. Oh.
Can you go back to that? I'm afraid I don't quite understand what goes on there. What if n is smaller than m?
So what if n? So m in particular is going to be smaller than m, of course. By oh, you mean I probably given d and n, okay?
Oh, okay.
What is the biggest m? So yeah, of course m will be less than n as the answer of this question.
So you want to know the large number that can work in any metric.
Yeah, I hand you an n-point metric space. Just because it has n points, the conclusion should be somewhere in there must be n points which are Euclidean, up to error 7 or whatever you want. Okay? It's not clear that this is possible, but it is because, well, in this original 1985 paper, Bourgain-Figiel-Milman not only asked the question, they also answered it. So this is what's known as the Nonlinear Dvoretzky Theorem. Of course, as I said, there is more than one version, but maybe I should say, so these are two problems. Both of them we know the solution of. So the complete solution of this happened in 2006, and I will describe it, including some applications. This is really very recent, from a couple of months ago. And one of the things which I personally found surprising is that, in some sense, I thought that the continuous version should come from a limit of the discrete version. But as I'll convince you in the end, these are just completely different questions. Okay? You'll see, okay? They are similar and different. So there depends on which, well, when I start saying theorems, you're going to see it depends on the distortion D, and there are areas where they're similar, they're similar, and there are areas where they're different. Okay, so.
Stupid question just to see
Yeah.
how different the linear and nonlinear versions are. Is it true that any finite metric space asymmetrically embeds in the Manor space, or no?
Yes, every metric space embeds in an infinity.
No, okay.
Yeah, so, yeah.
In the linear theorem, can you replace their exist with the for almost all linear subspaces?
Well, then the for almost all has to be defined. That's how it's proved, but that's how Dvoretzky's theorem is proved. But probably the cleverest part of Dvoretzky's theorem is coming up with a correct notion of almost all, for which you can argue. Okay, and actually, that's the whole proof in essence. So the meaning of almost all is the main point in Dvoretzky's theorem. Okay, so where was it? Okay, so the nonlinear Dvoretzky theorem. Again, the same paper of Bourgain. Says the following. So for every d bigger than 1, there exists some constant c of d such that any n-point metric space X has a subset Y with Y is Euclidean up to your error D, and the number of points is at least C of D times log n. So just from knowing that you have n points, you will always find a chunk of size log n, which is Euclidean. And this is sharp in the following sense. There exists some distortion D0, which, for a reason that you will see in a second, I check that their proof breaks down at this number. For which so you cannot do better. Let me introduce a tiny bit of notation. So let me just a tiny bit of notation. In this problem, let's call this M R of D and N. So R of D of N is the biggest integer such that in any n-point metric space, there is always a subset of this integer, which is Euclidean up to your error. R stands for Ramsey because this is a Ramsey problem. Okay? So what I said in words is that they're just saying that R D0 of N is big O of log n.
If you take a random graph and its distances will be only 1 and 2, then what will be?
That's exactly what they did. That's exactly their.
Okay, but where does the 1.023 comes from? I mean, I can see 2 or something.
Yeah, you know the answer also, but let me. I'm getting there. Yeah. So even these two requires an idea. I mean, I don't know if you can see it. It does use Johnson-Lindstrauss and things like that.
Yeah,
Yeah.
Yeah,
Okay.
yeah,
But yeah.
I'm talking about the law.
Yeah. Okay. But I don't think it's just trivial even. Okay. So okay. So this was I guess 1985, and it's very satisfactory. Actually, I mean, as a grad student, I learned this in a class as a Nonlinear Dvoretzky Theorem, and there was this D0. It seemed to be some fluke of the proof, but over time, motivated by really beautiful applications, which I will describe, there started to be evidence that something else is going on. So there was actually a big list of works, but I want to just mention a work of Bartal, Bolobash, and Mendel in 2002, which really, this is what got me very interested in this problem. So they proved that if you want a distortion log n, then you can get m to be at least 0.1, n to the power 0.1. So if you're willing, just the meaning of the number log n, I should just to put everything in context, let me just remind people of a famous theorem called Bourgain's embedding theorem, which says that any endpoint metric space you can embed, I guess, with distortion 20 log n x into L2, and this is sharp up to the 20. Okay, so we're fighting log. Log is the worst possible distortion of an endpoint metric space. So log is already non-trivial, and here you can get n to some power. Okay, and so this was an indication that something else is going on, and we indeed investigated this from several aspects, and in 2002, also with this group of people proved the following theorem. So as follows. So I guess it has.
So question. So this Bartal, so this applies to what? That one or that one?
Which one or what one? I can't see what.
So the statement you write there, it says that for every endpoint metric space,
Yeah.
you cannot do better than.
No. I'm saying for every endpoint metric space, you can find a subset of size n to the some power 0.1, which is Euclidean up to log n.
Okay. So that's
so
the standard way. The statement right above it. Did you? So you
I'm not. This is not really comparable because this is not a constant, but it shows that some.
No, but the thrust of it. So it says for every x,
Yeah.
it has a y.
Yeah.
And then for which you cannot do better than log n. This is for every.
This statement here, this says there exists a sequence. Let's interpret, let's get used to the notation, okay? What does this formula say? It says there exists a sequence of endpoint metric spaces such that all their subsets of size log n are non-Euclidean by at least this D0.
Okay, there exists an x.
Yeah,
Okay.
a sequence, yeah.
Okay, so that
Yeah, but that's not really, this is in the positive direction.
Okay, fine.
Okay, so
So it suggests a smooth curve of some kind.
well, no, that's what so let me tell you. So the first part is that if you give me a number d between 0 and 2, then this number r d n is at least some c of d times log n. Well, that's Bourgain-Figiel-Milman. I'm copying their theorem, but it's at most some other c of d times log n. And if d is bigger than 2, then this number, Rd of n, is at least n to the 1 minus delta d, most n to the 1 minus delta prime d, where these numbers, delta of d, delta prime of d, are in 0, 1. So the minute you pass 2, you get n to some power. And everybody asks me always, so d equals 2 is open. And all the variants of what's the repercussions of being open at d equals 2, we don't even know what happens when d is 2 plus epsilon, the correct asymptotics. Does the exponent, we're really way off in the bounds here. So we don't know what happens at
Yeah, just to understand the quantifiers, these inequalities means that for any set of metric spaces, the
Which one are we talking about?
Or both, actually.
So, okay, so,
For any and for some, right?
yeah, so a lower bound has for any, and an upper bound says you cannot do better. So there exists a sequence of bad guys. So the first part, the lower bound is Bourgain-Figiel-Milman. There is nothing new. All this is just pushing, like what Noga said, pushing it all the way to 2, and then you get stuck. And above 2, you can do really much better. And this really much better is going to be useful for us in a second. Okay?
The deltas go to 0 as d goes to infinity?
Yeah, I will discuss all of this. What we don't know is that delta goes to 1 as d goes to 2. Okay, but d goes to infinity, we know the answers. Yeah, so maybe I'll emphasize that d equals d goes to infinity. So this is the same. I'm just rephrasing what that theorem gave. In the case of very big distortion, which is the case that we care about, well, that's what comes up in applications. So the theorem is, now let me say it in words. So for every epsilon bigger than 0, any n-point metric space X has a subset Y with n to the 1 minus epsilon cardinality, and Y embeds into Hilbert space with distortion big O log 1 over epsilon, some function of epsilon. Okay, and this is sharp, so for every n there exists an n-point metric space Xn such that for every subset Y of X with at least n to the 1 minus epsilon points, if Y is in L2 with distortion D, then D must be bigger than a constant over epsilon. So up to this log, this is sharp. This is answering your question. So actually, it took a little bit longer to actually, we now know that this log is not needed. So Mendel and myself in 2006 proved, well, just got rid of the log. So this is the nonlinear Dvoretzky theorem for large distortion for every epsilon bigger than 0, and for every n, any n-point metric space has a subset of size n to the 1 minus epsilon, subset that embeds maybe a subset Y with okay, so that's the end of the story because of the lower bound over there. This cannot be improved, and this is the correct interplay. Now, why did I do this funny thing of stating two separate theorems if we actually knew, well, when I wrote that down, I actually knew that I don't need the log. The main point in this theorem, and this is what I want to spend some time on, is that this theorem, the proof is completely different. It's actually more similar in many senses to the original proof of Dvoretzky's theorem. There are really steps which are analogous, but the main point is that it gives much more, and we're going to need to understand this much more, so I want to say a few words about this proof. Okay? I should say, just before I pass to explaining what kind of structures we find over here, that there is really a whole lot to do, even in the context of just, of this problem, or let's say, in analyzing examples. So you can ask this question for any geometry that you care about. So for example, you can look at, let's say, 0, 1 to the k, so just the Hamming cube. And now you can ask the nonlinear Dvoretzky problem about this object. So you can ask, so this is with the L1 metric, the usual Hamming distance. So you can ask, so what's true is that if you want to, this guy, if you want to embed it into Hilbert space, you need distortion at least root k. But now I ask you, what is the biggest subset of the Hamming cube which embeds into Hilbert space with distortion 100? Okay, so that's and you can ask these things about lattices, and we actually care about these things. So for the Hamming cube, I'll send you to that paper. There is almost a solution up to logarithmic terms for this problem. But in every particular case, just like in the examples over here, so far we needed this involved some geometry. So there are interesting spaces, even particular families of spaces for which we do not know the answer and we care about it. Okay, so you can ask the general question, or you can ask about natural sequences of spaces.
So here, the biggest space will be a code, namely it will be a simplex, so all the distances will be the same if you try.
All the distances will be
Essentially the same. I mean,
yes, but you have to prove that.
Like
Yeah. But the embedding will be, well, yeah, okay. Yeah. There is some subtlety which I'll explain later, but yeah.
What is C? Do you know C?
Which is C over here? These are great questions. I'm about to discuss it.
Like a million or like 10? Where is it?
So in the original proof, it's something like 16 or maybe 60 or something like that. But we actually want to get C to be 2, right? That would be wonderful because that would explain the phase transition at 2. And it's amazing that you're asking this because this was something that I wanted to discuss. I'll get to this. So getting it to 2 was actually a major issue that, not a major issue, something that we can prove was impossible using that method. And we had to invent a new method. This is a paper from last year with Terry Tao, where we managed to get down to 2. Well, let me get to this, okay? Yeah.
The exponent, 1 minus epsilon is sharp, or?
Yeah, this is from over here.
Oh, okay, right.
This is, yeah.
I mean, similar statements.
I'm sorry. Okay, so I want to say a few words about this and how this is, and work out one application to computer science, and then hopefully have a little time to discuss the Hausdorff dimension. Okay. So I'll explain to you the logic or the structure of how we find these sets. And I need to introduce a tiny bit of terminology, just terminology. So if I have a metric space, and P is a partition, so here's X. So if I have a little point X, I'll always write by P of X it's the element of C to which X belongs. So this guy here is P of X. And I say that so P is delta bounded. Delta is some parameter. If the diameter of C is at most delta for every C, for every element, so all these pieces are at most delta. And there is a notion of a partition tree, which is standard. So, so a sequence pk is called a partition tree if, let me continue over here. So the first partition is just a trivial partition. Let's always normalize diameters. These are finite metric spaces, so I always normalize diameters to be 1. So pk is 8 to the minus k bounded. 8 is just something which I chose for convenience, because I thought I'll be able to show all the details of the proof. Probably you won't care, but any 1 plus epsilon, anything bigger than 1 here would work. So in the picture, this pieces is going to be, if this is the kth level, it's the diameter is 8 to the minus k. And 3 is that pk plus 1 is a refinement. Okay, so that just means that pk plus 1 of x is always inside pk of x. So this is just a sequence of partitions which become finer and finer. Etc. And the key concept that I want to discuss so much like the proof of the original Dvoretzky theorem, it's gonna be, so the original proof of this thing with the log was actually some deterministic procedure. It was some case analysis which eventually led to the subset. Now I'm gonna use, really similar to Dvoretzky's theorem, a random proof, and the random object is gonna be a partition tree. So definition. I have 2 parameters, beta and gamma. So a distribution over random partition trees so this is now a random object, is called completely beta padded with exponent gamma if for every point in the space I look at the following huge intersection. I look at the probability that for every scale k, the ball around x of radius beta times a to the minus k is inside pk of x. This has to happen for all the scales at once. This has to be at least, this probability is at least 1 over n to the gamma. So here's x. in the first level, the partition is the entire space and everything is fine. Second level, I cut the space into pieces of diameter 1/8, and I want an X has to think that it is 1/8 beta times 1/8 away from the boundary. And now I zoom in more. Now X thinks it's in this little piece here. And now the diameter is 1/64. And still it's going to be OK. So I'm going to look at draw a ball of radius beta times 1/64. That's still going to be inside its piece. And then I'm going to zoom in more. And now, OK, this is just a definition. So let me prove a very, very simple lemma.
So compared to the usual pattern decomposition where this is to be a constant.
The quantifier is outside.
Oh, right.
Okay, this is a quantifier is inside the probability. Okay.
So of course,
It will be clear when I actually prove how this is related to the problem.
don't go too fast. So your space is finite, so every tree is finite.
Yeah, eventually it
Only
stops.
bounded
Yeah,
and so on.
yeah.
And you just want to separate points which are very close at the later step because you want.
Yeah,
So
yeah,
that's all you
yeah.
want. Okay. And then you'll approximate it by ultrametric.
In ultrametric, yeah.
Okay.
Okay.
So you're going to eventually, I assume eventually you're going to prove that such things actually exist.
Yes. Don't worry.
So to get an intuition, so what this says is that in some sense this random partition is universal, locally universal.
A random family of partitions.
Well, but just saying, when you pick this random partition at X, it's kind of locally universal in that any partition tree is going to, the partitions at X are going to sort of interleave with the layers.
Why?
Because you're saying the whole ball with approximately a to the minus k radius around X is going to be contained in the kth level of the partition tree. And so that means
But it could be that for every X this happens. If you have a different partition tree, it's going to be with.
locally at X.
Yeah, but even for a given X, if you give me a different distribution, it could be that they're padded in a different part of the.
Property.
But the probability is very small.
Right, but when it comes up,
Yeah.
then for the partition.
Oh, if it comes up, yeah.
Then
yeah.
what it's saying about that
Yeah,
partition
yeah.
is that it's kind of
Yeah.
universal for the class of all partitions.
Yeah.
On that
Okay.
point.
Yeah. This is a. Let me just explain the connection, and then everything will be clear. So it's a lemma. So if X admits a completely beta padded partition tree with exponent gamma, then there exists a subset y of x with at least n to the 1 minus gamma points, and it embeds in Hilbert space with distortion, I think 8 over beta. 8 is just that arbitrary choice that I made. And let me prove it. So you take this random partition tree coming from that definition, and my subset y, I'm going to look at the random subset y, which is exactly these points for which it's happened. So y is going to be all the points x and x, such that for every k, the ball around x of radius beta 8 to the minus k is inside pk of x. And so the definition tells us that every fixed point is probability 1 over n to the gamma of being inside. So the expected size of y is at least n to the 1 minus gamma. And on this y, So on this y, so if I take 2 points, x and y next, x different from y, let, I guess, kxy be the largest k such that pkx equals pky. Where's my picture? So here is x, here is y. Obviously, they're different. At some point, they're going to be separated. I'm going to look at the last time they're not. And I'm going to define rho xy. This is a random number. It's a to the minus kxy. And what do I know? Well, I know that the distance from x to y is at most a to the minus k, because they're both in the same piece of diameter a to the minus k, which is rho xy. But I also know that here is x, here is y, here is the piece in, this is pk. I also know that by definition, at the k plus 1 stage, they're separated. So now if they're in y, then I know that this little ball over here is completely inside this piece. The ball around is a radius beta times a to the minus k minus 1, because this is the next stage. Okay? So this, in particular, the distance from x to y is at least beta over 8, a to the minus k. That's what's written over here, which is rho xy. So this is a small number. So the distortion from rho is 8 over beta. Okay, yeah, 1 second. Okay. It doesn't help in a general metric space, but it will help for something else. Okay, it doesn't help in a general metric space. It's a very important observation. And now the only thing you need to check is that rho is an ultrametric. Like the p-adix, or it just means that it's when you write the triangle inequality, instead of a sum, you get a max. And now an easy exercise that if I will prove to you in the break if anybody wants to see it, is that any ultrametric is isometric to a subset of L2. Okay? So actually, and this is going to be needed for the thing we're going to see in a minute, the subset that we find is actually an ultrametric. I erase it, but in all the so these are special subsets of L2 which have additional structure that we're going to use. These are Cantor sets. But keep in mind that in all these theorems that I stated, the impossibility results are for arbitrary subsets of L2. So essentially, in this generality, there are metric spaces for which the best thing you can do is just embed them into an, even though you're allowing all of Hilbert space, the best thing you can do is embed them into a Cantor set. Okay, but okay, so that's that. And of course, very, very justifiably, I need to, this was abstract nonsense. All of the geometry goes into proving this. And I want to put this aside just for a moment, just to explain something about this structure that we found here has consequences that I want to say a few words about. And I'll explain to you how you find this. This is where the geometry hides. Okay. So as Noga said,
So it doesn't really matter which will be the gamma. Any gamma will work, right?
what?
The sequence of distances in ultrametric, as you define, the sequence of powers of some fixed gamma. So you don't care.
Yeah, I don't care. I had big plans of proving this theorem for you. And this morning, the proof that I got gave me an 8, so I chose 8. I could have written 3, and that would have been a different proof. Okay? Yeah. This is completely arbitrary. Okay? It's coming from what I plan to show you. Okay? And probably I'll show to some people in the break. But okay? But this is just completely arbitrary. 3 would work. 2.1 would work.
will not get lunch.
Fair deal. So where was I? Okay, so Noga said something very important. The subset Y, so here's X, here's the subset Y that we found. The subset Y has an additional property. It's not that this is inside here I have this tree structure or the original metric is equivalent to an ultrametric or the same thing as to a tree, to leaves of a tree. The subset Y actually has the property that it can be used to compute distances from a point in Y to any other point outside, right? Because in this argument, I just used the fact that X was in my subset Y to get the distance, and Y could have been any other point, right? So the subset Y is not only equivalent to a subset of Hilbert space or an ultrametric, but in addition, there is some ultrametric defined in the entire space with the property that I can if I compute the ultrametric distance or the tree distance between X and any other point, doesn't matter if it's in the subset or not, it's still going to be the correct number up to the error that I'm allowing. Now, why is this relevant? So let me show you very quickly. So these are very different applications in the original applications that nonlinear Dvoretzky had. So there is a problem called the proximate distance oracles. And let me just show you very, very quickly how this actually solves it up to constants. So now this is a computational problem. So if you're giving me, if I'm given an n-point metric space, then of course I can store all these numbers. Let's call Aij so X is just the numbers 1 to n, let's say. It's a distance from I to j. So I can store these n squared numbers, and then I can compute the distances. If somebody tells me what's the distance from I to j, I can look at these n squared numbers, the ij entry, and give you the answer. In the approximate distance oracle problem, so I guess roughly speaking it's can we store little o of n squared numbers and still be able to answer distance queries fast. So what's a distance query? I want to somehow store less than all the information in the metric space in such a way that when somebody comes to me and says, what's the distance between point number 17 and 1003? I will look at this not enough information that I stored, and I will spit out a number which will be the truth. So we will assume distance query is fast up to a specified error, right?
So now you want Y to be small, not big,
Y?
right?
What is Y?
This Y.
No. I want it to be big. So in a very famous paper from late 90s, I think, Thorpe and Zwick proved that this is actually possible. They proved that for every k, you can store n to the 1 plus 1 over k, big O, I think k times this, never mind, numbers, and answer distance queries in time big O of k up to error. Okay, so I can remember, k is 100, I can remember n to the 1 plus 1 over 100 numbers, such that if you come and tell me what's the distance between 17 and 1003, I will think, let's say, time k, whatever my error is, and I will get an answer up to multiplicative error k. Okay, I will spit out a number which I know is a truth up to this factor k. Now, so this is really a beautiful result and a beautiful construction. Our contribution is the observation, which is actually a very, very different approach from what they did. Is the observation that we can use nonlinear Dvoretzky theorem, and it will take me really a second to convince you that this is possible, get the same thing, except that this O of k will become O of 1. It will be just like storing the matrix. So if you want up to error, okay, so the theorem that I want to convince you, and that's the corollary of what we did, is that possible to store n to the 1 plus 1 over k numbers and answer queries in time big O of 1 up to error, again, multiplicative, big O of k. So let me explain to you how this is related. So here's my metric space. And I'm going to use a nonlinear Dvoretzky theorem, what we just proved, sketched, and find the biggest possible piece that I can get, which has the biggest possible y, which is this distance computer. Okay, so this is the first one. I get a y of size at least n to the 1 plus 1 over k. And what do I know about this subset here? Minus. And what do I know about this subset here? I know that there is some tree metric, somehow defined in the entire space. This is this random partition, actually, such that if you give me a point in the subset x, and you give me another point here, so this was bad, let's do that. Okay, so you would look at the least common ancestor, and that will be their distance. So, and that will give you the truth up to factor big O of k. Okay, the truth, okay. So, fine. So let's find this big subset and let's write down the tree corresponding to this big subset, whatever it is. Let's look at what's left. And again, take the biggest possible subset we can find. So this is now n to the 1 minus 1 over k.
Where did k come from?
What?
Where did the error k come from?
In the theorem. The theorem said that there was the beta, the 1 over beta. There was an error. I deleted it.
Yeah, what was beta again?
Well, in the theorem, so I should say that the geometric construction is that you can get this to be 1 over k, and beta to be also a constant over k. Okay, you can always do that. Yeah, that's what the parameters, the statement of the theorem implied, but it didn't say it. Thank you. Okay, so I can, and of course I'll continue. And each time I get a tree, this is defined, this tree is going to be on this part of the space, not the first part I took. I'm going to write it down. Then I'm going to take the biggest piece I can find here, write down the tree. I get an array of trees. Now somebody hands me 2 points, x and y. Okay, let's look at the first time that x appeared, let's say here. This means that y is somewhere later. Okay, but this tree, x works for all the other y's. So to compute their distance, I need to find the least common ancestor in this tree, in the array of trees. And, well, I guess it's famous, but there is a famous data structure of Arel and Tarjan from when? 1980s or 70s? 80s or 70s? Okay, early 80s, which says that if you give me a tree, any combinatorial tree, you can always store big O of n numbers. N is the number of vertices. Okay? You can store big O of n numbers in such a way that if you hand me 2 leaves, I can tell you in constant time what is their least common ancestor. Okay, so this is a really beautiful fact about trees. So what we really do is we find this using this random construction. This big piece here, biggest piece we can find here, biggest piece we can find here, right? And now for each of these trees, we do this Harel-Tarjan rewriting of it, have this array of numbers, and then we're done. We got our approximate distance oracles. Okay? So we definitely want, okay, and now the only thing that we need to check is that you crunch the numbers and you get the number. Believe me that the numbers that I wrote down is what you get from this iteration. Okay? So it's very, very simple. And it's very different. So what Torup and Zwicker are doing, they're trying to find, in essence, sparse subsets. And we're the opposite. We're trying to find big structured subsets. Okay? It's not really, it's really conceptually a different kind of construction.
Does this theorem come with some kind of lower bound? Because
I'm about to write it. It's a really, yeah, it's fun to give a talk here because I'm listening to my own talk. Yeah.
So, in what sense is it constructive? Because
oh, so of course I didn't tell you how I found this random partition, but this is all algorithmic. Okay. Because I didn't prove the theorem, you didn't see it, but this is just done by hand.
Is this FRT type or?
It's an FRT type. No, CKR. Yeah, but you have to really do a new kind of analysis of it.
Yeah.
Yeah.
So the current analysis would work with like if the aspect ratio was bounded, like polynomial or something.
I don't see that.
Even that.
I don't see that. Maybe, but I'll explain to you later. But I don't see that. Where was I? Yeah. Yeah, I want to say the lower bound, then I want to say that, because now I'm still in 206, and I want to say 1 minute afterwards and something new, but it will be really 1 minute. But the lower bound is actually from 209. I found this quite surprising. It's due to Zommel, Verbin, and you. And they just proved that any data structure that answers distance queries, answers distance queries in time t up to error k has size at least n to the 1 plus 1 over c over k times t. Okay? So, and this is in the cell probe model. This is a communication complexity lower bound. This is, so what you see is because our time was constant, this matches the upper bound. And if we couldn't, let's say if you use the old Torup-Zwick thing, you would get 1 over k squared, because the time was also k. So in essence, this tells you that this nonlinear, this geometric nonlinear Dvoretzky approach, maybe there are other algorithms, but no algorithm will do better than what we just showed you, up to the constants, and people do care about the constants. Okay? Now, there is another older, in the original Torup-Zwick paper, this is easy, but they also prove that no oracle of size little o of n squared answers queries up to error strictly less than 3. Okay, if you want the truth up to error 3, you need to store all the n squared numbers up to constants. And what this says, so actually we worked on it quite a lot, and we actually knew this theorem and didn't realize that this, I don't know who asked me about the constant. In the theorem, we had n to the 1 minus epsilon points and distortion to c over epsilon. And the question is, can we get this c to be 2 so that we can actually go down to the phase transition in this argument? And the answer is no, because if it would, I mean, if it has this additional property that it's like computing points from a point in the subset to any other point, then it would give a distance oracle if you just crunch the numbers, which beats what we know is impossible.
So what it's also saying is that if I was constrained to using a data structure of size n to the 3 halves, I'm screwed. I'm not going to get any improvement.
Yes. Okay, so, but it also says that we were doomed to fail. Actually, we really tried to get down to 2, and because of completely these computational reasons or combinatorial reasons, we couldn't succeed to do this.
So this needs a 3. This gives a lower bound of 3 to this concept.
Yes, but what I do want to say is that in 2010 with tau, we did manage to find a very simple random proof which goes down all the way to 2. But of course, because of these computational reasons, it cannot do that. Okay, and so but this is a different story. Okay. Yeah.
What goes in instead of this approach? Some infinity principle, non-computable? What goes in instead?
No. Everything is still computable. But the subset that we get, we give up this property that we give up the property that if you have a point in y and a point in this capital Y and a point outside, that the ultrametric approximates their distance. We just forget about that. We can't do that. We have to come up with a different type of construction which somehow will not be able to deal with that issue. It will have to use the fact that both of them are inside.
But still,
okay?
The bottom line, you will have some ultrametric.
It will be still an ultrametric, but it's gonna I mean, this thing with the padding automatically deals with points outside. You just have to give that up. That's all I'm saying. Okay, so I'm over time. Can I have 1 minute to tell you what the answer to the nonlinear Dvoretzky problem? I did start late. Yes, because this is the only thing which is not from 206 that I wanted to talk about. Okay, I don't need that much. Let me just tell you the answer. So first of all, so here is a theorem, a very new theorem of Mendel and myself, which shows that there is something happening. So which answers a Tau's problem. So for any alpha bigger than 0, and for every epsilon, any compact metric space of Hausdorff dimension alpha metric space X has a subset Y closed if you want. Of Hausdorff dimension at least 1 minus epsilon times alpha, and Y embeds with a constant over epsilon into an ultrametric. Okay? So if somebody hands me over some fractal of dimension, those of you who don't know what Hausdorff dimension is, they'll see the definition in a second when I explain what's going on. But if somebody hands me over a fractal of dimension 1000.37, and they want to find inside some compact subset of dimension 1000.31, I'll be able to do it. And I can make it be Euclidean or even an ultrametric up to my prescribed error. Okay? And so just because I know that some people are not familiar with these notions, let me tell you what is the, let's say, the ultimate Dvoretzky theorem. So what is the connection between the finite and the infinite? So this is actually, I think, a basic fact in measure theory. And here is our real theorem. And this is a statement about metric measure spaces. So the X, the mu is a metric measure space. So this is just a measure, a metric space with a measure, with a Borel measure on it, positive Borel measure. And I have a number epsilon as usual. Then there exists a subset Y such that, first of all, Y embeds with constant C over epsilon. Maybe I should say, let's start here. For every epsilon, there exists a constant C of epsilon such that for every metric measure space, there exists a subset Y such that Y embeds into ultrametric or L2 with distortion 1 over epsilon. And 2, Y has the following property. For every covering of Y by balls, so I have a family of balls which cover Y with arbitrary radii. We have the following inequality. Sum over I. Now what I do is I measure the measure of the ball around xi of radius c epsilon ri. Raise this measure to the 1 minus epsilon, I get at least the measure of x to the 1 minus epsilon. Okay? So let me put it up. So this theorem contains many of the things I said and many other things as special cases. So let's just look, for example, at the case when x has n points and mu is the counting measure. Okay? Then, and a very, very special case, just all the ri's are 0. So I'm covering y by singletons. This is just all the points in y. Okay? In this case, I'm just saying the size of y is at least n to the 1 minus epsilon. Okay? So this is, in particular, the theorem, the nonlinear Dvoretzky theorem with sharp dependence on epsilon. So now let me explain to you the connection with Hausdorff dimension. So how many people here know what Hausdorff dimension is? Okay, so do I need to define it? Let me just prove it to you. So if the Hausdorff dimension of x is at least alpha, then there is one of the only tools to bound Hausdorff dimensions from below, completely standard in analysis, is what's called the Frostman lemma. And the Frostman lemma says that in this case, there exists a positive measure, positive Borel measure, mu on x, such that the measure of a ball around x of radius r is at most some constant times r to the alpha for every x and for every radius. Okay, so having Hausdorff dimension at least alpha means that you can come up with a measure which has growth at most r to the alpha. Okay? So now let's take this measure, which it's a non-trivial construction, and apply it and apply the theorem to this measure. Okay, to the Frostman measure. So for this particular measure, that wasn't a good idea.
Should this be other way around?
No.
Dimension is upper boundary by alpha and
No. That's the statement of the Frostman lemma. I said it's positive, so I mean 0 you can always get, but you can get a positive measure with this problem. Positive I also mean, yeah, that's all.
Assuming the dimension is large or assuming the dimension is small?
Large. the way it's written, okay? So now let's apply it. What do we get? We get a subset Y, okay?
X is compact, right? People are confused because they're thinking of R the alpha.
X is compact. No, but that's not it doesn't matter if it's compact or not. Then you will have the measure support in a compact subset. It can't be that this is what's confusing people. Okay, well, good try. Yeah. Let me do the argument and you'll see. So I found some measure from the sky coming from Frostman's lemma. And now I'll apply the theorem to this metric measure space, okay? So I get a subset Y with the property that whenever you cover, so if a family of balls cover Y, then sum the measure right? This is just a statement, I copied it. Well, I'm going to use the only thing I can, which is I have a growth bound on the measure mu. So I get up to these are all constants. This is the sum of Ri to the alpha. To the alpha times 1 minus epsilon. Now, what did I just prove? I proved that no matter how I cover my set by balls, the sum of the radii to this power is bigger than some constant independent of the covering. The smallest power that you can put here, the infimum of those powers, this is exactly the Hausdorff dimension. Okay? So now you see the difference between the Dvoretzky problem for Hausdorff dimension and somehow the Dvoretzky problem for just cardinality of the points. We have to, this is somehow caring about the case when the covering is trivial. And even in the finite case, we have new information now. We know this for this kind of inequality for all possible coverings of the space. Okay. In particular, this already hints for those of you know that this random, I have no idea how to make the randomized proof work. I don't know how to argue about the random event for every covering something happens. So we're back to a hands-on deterministic constructions, which are, so I guess they are types of Calderon-Zygmund decompositions, things that people do in fractal geometry all the time. And yeah, well, I don't have time to discuss it, but there is actually, it turns out that this version of the theorem is really, the proof of it is incomparable to the other proof. You have to do something very new, but it does imply it. It's a very, very special case. And I think I'll end here.
Two short questions.
Yeah.
One is, so this whole alphametric approach means that you don't have any control over the dimensions of the L2 you're embedding to.
Yes. Well, what do you mean? For endpoints?
I mean the lambda.
But for endpoints, you have the distortion and the number of points, and
Yeah.
they somehow interact, right? Because maybe you can embed.
Yeah, but any endpoints in Hilbert space embed into L2 of dimension log n. This is the Johnson-Lindstrauss lemma.
Right. So if you want to control dimensional L2, you'll have to lose some other log term.
No. I mean, I can get them into dimension. Oh, you want to insist on a fixed dimension? Let's say 100.
Well, or
No, you lose much more than log terms. This is going to become impossible to do actually.
So that was
Yeah.
one question.
No, we need infinite dimensions.
For this lower bound and with K and T and all that.
Yeah. So
So is there a way to, in fact, in your proof, to trade off the running time for the error?
the running time for the error,
Well,
the running time was a constant.
But suppose I'm willing to compute for longer if I don't want as big an error. You still can, because the lower bound mix them together, right? It's running time.
Oh, but well, okay. So what the lower bound was n to the 1 plus a constant over the error times the time.
Right.
And what do you
Spend more
want?
time to get lower error. Can I do that or no?
I want to spend more. You cannot get error below 3, for example, period, with little o of n squared points. Okay, that's
If I resign myself to this fact, then
if you ignore, if you what?
if I resign myself to that, and
Yeah.
suppose that I want to really have space, n to the n log n or something, and they want to compute longer to get lower multiplicative error. Can I do that or no?
So so you want n log n. The best thing I can do to tell you is what's known. I mean, we know n to the 1 plus 1 or c over k, and you can choose the k that makes this log n. So
I know, but you can do error O of k, but running time O of 1.
Yeah.
Suppose I was willing to spend running time O of square root of k, can I then get the error to?
I see what you're saying. Maybe. I don't think anybody ever thought about. No, I don't think anybody ever tried to go to the torp. We can try to get the time to be root k and then pay k squared in the error. I mean, you can't. No, conceivably you can do it. I personally don't know of anybody who ever tried to do that. But yeah, there is a whole. Yeah, definitely. I should have said that in the Hausdorff dimensional theorem. Here we also have constructions of fractals which show that this is sharp. Okay, so and this is in itself it's some sort of fractals that come from expanders. So it's a way to take expanders and build a fractal out of them. Things, continuous objects with big Hausdorff dimension. And yeah, maybe the other thing is,
From discrete expanders.
yeah, but then you go to a limit in a certain way, and you get to, in the end. This is but this is sharp. All I'm saying is that this is sharp as well. Yeah, and maybe I'll let you guys guess, try to think. In the finite world, there was this phase transition at 2. What do you think happens there? In the Hausdorff. Yeah, yeah. So yeah, so if you want by Lipschitz distortion less than 2, or does anything happen at 2?
Probably below 2, you don't get.
So what happens to the nonlinear Dvoretzky theorem, the tau version of the nonlinear Dvoretzky theorem, below 2 is that the answer is exactly what you said. If you want distortion below 2, the answer is it's impossible. We can construct arbitrarily large n-dimensional compact metric spaces of Hausdorff dimension n with the property that if you give me a subset of them and you tell me this subset is Euclidean up to an error of 1.99, then the subset has dimension 0. Okay, so you just get nothing. What happens is that it starts at 2. And in this sense, I think historically it was very lucky that the questions were asked in this order. Because this phenomenon of Bourgain-Figiel-Milman simply doesn't exist in the Hausdorff dimensional version. They wouldn't have gotten 1.023 log n points. There is no analog of this theorem. Well, yeah, probably there is an analog if you do something like logarithmic Hausdorff measures or stuff of that type. But yeah, okay.
What was this 1.023? So just the fluke of the proof, right?
It was. Well, I'll explain to you later. They didn't do the random graph argument that you are saying. They did some other type of argument in which they used the Ramsey theorem for. I'll show it to you later. But it wasn't the random graph argument, and yeah, that's a. It's a fluke,
Okay.
but yeah.
How do you get back the classical Dvoretzky theorem from your version?
I don't.
You don't.
So this is a good question. I don't know. I actually don't think this is, apart from saying this is an analogous question, and even the methods of proofs are analogous in certain senses. I don't see a connection, and even more so, we get a contour set, okay, and Dvoretzky gets a plane, but in the applications we use that this is a contour set. Okay, so it's not only that it doesn't imply Dvoretzky's theorem, it gives something else which we need that something else. And so in the end, you can view the Dvoretzky theorem as something that motivated people to ask a good question, rather than, I really don't know how to get back to Dvoretzky's theorem.